this lecture we'll talk about again on multi-carrier modulation. We will continue from part 1. So we discussed that the window of time associated with the detection of in multi-carrier signal is given by n over b. This n over b is the time period of integration when we integrated it at the receiver side. So hence MCM or multi-carrier system transmit n symbols using n subcarriers in the time period n over b. So this means that we transmit n symbols in time period n over b. So the symbol rate would be here not as 1 over 1 over b, but it would be equal to n over b. So again that would turn out to be equal to b. So if we compare this with the single carrier systems, the overall symbol rate does not change. So the symbol rate in single carrier compared to multi-carrier system is unchanged, it's the same. So if we have n over b, this is the complete MCM symbol given, or the block of symbols which is spread over n over b. So it means that n symbols or n subcarriers. So in single carrier systems we have one symbol on 1 over b subcarriers. So overall the data rate is invariant. In MCM we have n symbols transmitted in n over b time. So in single carrier system we transmit one symbol in 1 over b time. So now we look at the transmitter and the receiver structure of MCM or multi-carrier systems. We transmit symbol, we have a serial to parallel, or we have a demultiplexer which converts the serial data coming into parallel data. So it means that we are trying to transmit n symbols in parallel. So we have bank of modulators. Each modulator is producing e to the power j 2 pi I L subcarriers. So each data is multiplied with that bank of subcarriers, that is ith data stream is modulated onto ith subcarrier, and then again the output is in parallel. We sum all the outputs from the bank of modulators, which is basically giving you sum of all the subcarriers. We get a composite signal here, and that is sent to the channel. At the receiver side, we have YT from n subchannels. What we have to do, we have to basically multiply each YT with different demodulators. So we need to repeat this YT so to produce L number of YT copies. So that is why we have a repeater here, or it's kind of serial to parallel converter, but all the parallel items are the same YT composite signals. So we have bank of correlators here. Those bank of correlators are being multiplied with each copy of same YT. So this is called coherent demodulation. So this produces e to the power j 2 pi FLT conjugate, or e to the power minus j pi 2 FLT, ranging from for all else. Then we have parallel to serial multiplexer, which converts this parallel data into serial data, and we get a symbol stream here. Now consider a bandwidth of 0.024 megahertz, or equal to 1024 kilohertz. So this is a single carrier. Now assume that most of the time, as we have in wireless systems, we have bandwidth greater or equal to coherence bandwidth. The channel does not remain the same for all the frequencies, as we discussed in the fading systems. So normally coherence bandwidth is in the range of 200 to 300 kilohertz. So 1024 is quite large and 300 kilohertz. So hence single carrier systems would be experiencing inter-symbol interference. Now again we assume that B is equal to 1024 kilohertz and N is equal to 256 subcarriers. So we have divided the bandwidth into 256 subcarriers. So bandwidth of each subcarrier would be given by B by N, that is equal to 4 kilohertz. Now this 4 kilohertz, if we keep the coherence bandwidth the same, is quite smaller than 300 kilohertz. So ISI or inter-symbol interference can be reduced. So B by N is smaller than B or C. Each subcarrier experiences flat fading. So that is the main objective of multi-carrier modulation, is to reduce the bandwidth of each symbol so that it does not experience inter-symbol interference, and each subcarriers basically is experiencing flat fading compared to non-flat fading here in a single carrier system. So no ISI is introduced in time domain. So what is the bottleneck in the MCN system? The bottleneck is that the implementation bank of the large demodulators or modulators at the transmitter and the receiver side is challenging. So if you increase the number of carriers, the bank of modulators would increase exponentially or quite large. So in this regard, to overcome above challenge, a key advancement was made by Winston and Ebert in paper titled Data Transmission by Frequency Division Multiplexing using discrete Fourier transform in 1971 by Bell Lab engineers. Winston and Ebert were Bell Lab engineers. What they did is they basically did the following. Consider the MCM transmitted signal with a band limit to B Hz. So hence the Nyquist sampling rate is B. Sampling time would be given as 1 over B. So the composite MCM signal is given by this equation. Now consider the UH sample of this ST. UH sample means that we sample this TS at U time intervals. So now T would be equal to U, TS is equal to U over B. So instead of transmitting signal directly, the composite signal directly, we sample it at Nyquist rate corresponding to B samples per second. So SUTS would be equal to XU. So that would be equal to sum of I xi e to the power j 2 pi I b over n into u over b. So at the end of the day we will have this. Now this thing is basically called the DFT of the information symbols. Yes, you may also have studied this in digital signal processing course. So the samples of MCM signal are x0, x1, xn minus 1. So now st would be equal to sum of xi to the power j 2 pi b over nt. So this is the ith stream, this is the ith subcarrier, this is the MCM composite transmitted signal, where now Ts is equal to 1 over b. So UTS would be equal to U over b. So time instant of the UH sample would be given by UTS is equal to U over b. So instead of sending XU, you send XU is equal to SUTS is equal to SU over b. So now you have instead of T, you put U over b. So B and B would cancel out each other, you will get this signal. So this is IDFT of the transmitted symbols. So IDFT stands for inverse discrete Fourier transform, and IFFT stands for inverse fast Fourier transform. Fast Fourier because it is a fast algorithm to implement IDFT. So this is basically the sampling of the composite signal at the Nyquist rate gives the IDFT. So this basically IDFT and IFFT, they form the basis and they are different from the multi-carrier modulation scheme, and they form the basis of the OFT. Thank you.